Hey everyone, welcome back to part two. Welcome back to part two of the exponential growth and decay. We're going to look at example 6 as well. Sorry about that, we're not going to the first page yet. We're going to use the formula, and we're using the one from our formula sheet, which is y equals ab to the t over p. Okay, and because they mention half-life, the half-life right away tells you that our base on our power is going to be 1/2. And this, the 7 years, is our p, our period of time for the half-life. So we can put that into our equation. Okay, so p is 7, and like that. And what else do we know? Determine how much of the isotope must initially be present. Okay, so we're looking for the initial amounts. We're looking for A. That's what that's asking. To decay to 60 grams. So the final amount, 60 grams in 14 years. So the time on the top here is the amount of time for that to happen, and this time on the bottom of the exponent is the amount of time for that, the b value to happen. Okay, let's go about simplifying this. Now, let's take a look. 14 over 7, right away we know that's 2, so let's change that to 1/2 to the exponent 2, and then we can square the 1/2, so we would have 60 equals a square the top, square the bottom, so 1/4. And then finally we're going to divide both sides by 1/4, otherwise known as multiplying by the reciprocal, 4/1, and we would get 240 for our value of A. Now let's look at the units. A was the initial amount of the isotope, and it decayed to 60 grams, so our initial amount would be grams. Okay, now we're not going to do part B, but it says on part C, in this particular example, explain how the solution to the problem could be found without any formula. And some of you may have picked up on this already. If it has a half-life of 7 years, so if we start, after 14 years, so we start at time 0, and then half-life of 7 years, and then they're asking about 14 years, right? Okay, so if we had 60 grams after 14 years, then 7 years before that we would have had twice as much, so it would have been 120 grams. And 7 years before that we would have had twice as much again, 240 grams. Okay, do you see how that works? 240, half of it, and half, and that's how half-life works. Okay, so every 7 years, in this case, half of the amount of radioactivity of isotope was remaining. All right, good job. Let's look at the percent ones now, and we're going to go back to page 1 for that. All right, so we're looking at example 1 now. In 2012, the university population of the country was 160,000, okay, in 2012, and was increasing at an annual rate of 4.5%. Okay, so this time we're increasing at a particular rate, a percent, and we're going to not do part A, and we're going to use y equals ab to the t over p, like we've been doing on the other ones. The difference on this one is b, because we're talking about a percent. If we're increasing at a certain percent, think of it as 100% plus 4.5%, which is going to be 104.5%. And then if you change that to a decimal, that would be 1.045. So divide by 100 to get it out of percent. So that tells me that my B value is going to be 1.045. Okay. The time that the T is going to be, in this case, they want number of years. So we're going to use N instead of T. Okay. Our P value, it says increasing at an annual rate. So that means our P, our period of time for it to have that rate, is 1 year. Okay? So that means this would be like over 1 in the equation. Okay, now what goes in front? Our initial amount. Did they tell us the initial amount? Yes, they did. 160,000 would go in front as our A value, and they want us to use P for population instead of Y. Okay, so there we go. And this n over 1, you don't really need that. You could just write that as n. Okay, now follow-up question. Determine the population in the year 2015. So 2015 is 3 years So t, or I guess n would equal 3 years. And all we do then is simply sub that in to our equation, and then we grab our graphing calculator and we figure out what that would equal. So let's do that. Okay, so we put that in our graphing calculator, 160,000 bracket 1.045 to the exponent of 3, and we should have gotten this. Now, this is population, right? So does it make any sense to have 0.58? No, you can't have 0.58 of a person. So we would probably round that up or down, actually maybe down, 182,586, and that would be people, I guess, or students. Okay, part D, if the population continues to grow at this rate, determine the number of years to the nearest year for the population to double from its size of 2012. So double from 2012 would be 2 times 160,000, which would be 320,000. Okay, and that's going to be our final amount, our P. Okay, so we'll have our equation. We still have 1.045 because it's still growing at that same rate, and we want the number of years, which is our n value in this case. All right, so we need to solve this. First thing we'd want to do is divide both sides by 160,000 so that we can isolate our power. So we would have 2 equals 1.045 to the n, and then we're going to log both sides so that our exponent of n can come down front. Okay, and then finally divide log base 2 divided by log 1.045, so we can get the n isolated on the right hand side, and off to the calculator to figure out that value. Okay, so when we put that in our calculator, we should have gotten n equals 15.7, or if they want it to the nearest year, so we'd say 16 years. Okay, hopefully you got that as well. Let's look at the next example. Next page, please. Okay, last example, example number 2. The number of fish in a lake is decreasing by 5% each year. Okay, so that means our time period is 1 year as a result of overfishing. Okay, if the number of fish present is an exponential function of time, state the base. Okay, so because we're decreasing by 5%, we would take 100% minus the 5% this time to get 95%, and then divide by 100 to get it out of a percent, which means our b value would be 0.95. Okay, so if we write that as an equation, we want t number of years. We're going to use n naught instead of a. So normally we would use this formula from our formula sheet. They want n naught subscript 0 to represent the initial population. So that's like our a value. N of t to represent our final population. Our b, as we've discovered in part A, is 0.95. And our p value is 1, so we don't need to write t over 1. And there we go. There's our equation. Okay, part C. If there are 2,500 fish present in 2012, June, how many would you expect to be present in 2017, 5 years later? Okay, so that means t is going to be 5 years, and they're giving us n naught. Okay, so n at 5 years would be 2,500, 0.95 to the exponent of 5. Okay, off to your calculators. Let's get a number for that. Okay, so we should have arrived at 1,934 fish were present 5 years later. And that makes sense because we're decreasing by 5%, so we should have gotten a number smaller than 2,500. Okay, now, how many years to the nearest tenth would it take the population to reduce to half of the number in June 2012? So if the June 2012, our initial amount was 2,500, then 1/2 of 2,500 is going to be 1,250, and that's what would go in for n, our final number there. Okay, our base is still 0.95, and we're still to an exponent of t, and that's what we're looking for. It says how many years, so t is a question mark to the nearest tenth. All right, so we need to solve this. First thing you want to do is isolate that power, so we're going to divide both sides by 2,500. That gets rid of that. And then we're going to, so that'll give us 1/2 on the left-hand side. Okay, so now we're going to log both sides so that we can get that exponent of t down front using our power rule for logs. And then last but not least, we're going to go log 1/2 divided by log 0.95. Okay, and into the calculator, let's do that and get a number, and then we are finished. All right, so did everyone get 13.5 years? All right, good job. Okay, so we're not going to do example 3. It involves E, and so we're going to skip that. It's not in the curriculum. And yeah, so hopefully the assignment on lessons 2 and 3 now go great, and we'll talk to you in the next one. See you guys. Thanks for listening.